Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 54, we will talk about last mile logistic, and we will first cover, it would be done in two parts. So, this is part 1. So, the different concepts that we will look at is, we will look into what last mile logistics is all about. Then we will look into the transportation problems. We will try to solve the transportation problems, and transportation problems are required both for last mile logistics as well as normal all logistic problems. We have discussed it in the last lecture. So, we will use 3 methods. We will learn 3 methods: the northwest corner method, least cost method, and Vogel's approximation method. This is to solve the first part of the transportation problem, where we find one of the feasible solutions, and then we will use optimality test using MODI or UV method. So, this is the method that is finally used to get the optimal solution, or which is the most optimum route, or this that solution to the transportation problem. And then, as discussed in the last lecture, we will try to show how to solve a transshipment problem by converting it into a transportation problem as well. So, when we talk about last mile logistics, as you can understand, it's the final part of the supply chain, and it is of course a part of the logistics. Then logistics include also last mile logistic, and we can define it by saying the last mile may be defined as the final leg in a business to consumer supply chain before the product is either delivered to the consumer, collected by the consumer, or collected from the consumer. So, see, previously this part was not there, not even this part was not there. For example, we have a delivery center, from there I go and deliver it to the customer, or that is the last mile logistics. Then actually what happened, then we say that sometimes going to individual houses probably will take up a lot of time. So, instead I delivered to a collection point from where the person can, or these individuals can come in and they can collect their particular delivery. So, that means that will actually reduce my the total cost of the system, and the individuals also need to travel a bit. So, there is also some amount of inconvenience added to their particular this collection process. And finally, it could be also collected from the consumer. Why? Because some people also return goods. So, that means the goods has to be collected from the consumer and again returned back to the entity which is actually sending that particular good. So, this is how we can define last mile logistics. So, as you can understand, this collection center concept, I would not say this has been very recent, but in this concept in that when we are talking about earlier, it was like if I could go to the post office to collect to check my mailbox. So, that is sort of, our individual goes back and then he collects from the particular post office instead of the postman coming and delivering it to my house. Or it could be collected from the consumer, like against people used to return goods as well. But now because of e-commerce, these terms are very, very prominent, because if I give the option to collect from a particular center, then probably the charges would be reduced. If then certain goods have got a option that you can also exchange it within a certain amount of days, even though if the good may be good, but if you don't like it, you may also return it. So, that kind of options actually has increased the this kind of aspects also needs to be considered in the supply chain. So, depending on the origin and destination, last mile could be classified into several categories. So, this categories has been done by myself and one of my research scholars. So, if I start with warehouse, and so I can obviously go to home to deliver. So, this is the centralized extended last mile. And then if I from the retail store, I can also deliver to home. So that is called hyperlocal. And from home, I can also deliver to another home. For example, somebody is selling a goods in either OLX or this kind of websites, where you can actually sell a good to another customer as well. So C2C is also another form of extended last mile. And OLX will probably come, and then they will transfer your goods from your house to another house. So that is another form of last mile. And from collection point to home, that is not there. Then warehouse to collection point, that means instead of home, I deliver to a collection point from where the customers will come and collect. So that is centralized semi-extended last mile. So then retail store to collection point, decentralized semi-extended last mile. And then because it is centralized, because it is coming from a warehouse, decentralized because it is coming from retail store where it has already got from the warehouse. So then from home to collection point, this could also be happening. Then C2C, semi-extended last mile. Collection point to collection point, not there. Then warehouse to retail store, this is the traditional last mile. This was earlier there. That means goods used to come to the retail store and people used to go and buy the goods. But this has been now replaced by home deliveries. So that is where this we are calling it the extended last mile instead of the standard last mile. So then retail store to retail store, not there. Home to retail store, this is reverse decentralized extended last mile. Why reverse? Because I am returning the goods. So that's why it is reverse. Then from collection point to retail store, that is reverse decentralized semi-extended last mile. That means the customer returns to the collection store. From there, it is returned to the particular retail store. Then warehouse to warehouse, not there. Retail store to warehouse, not there. Home to warehouse, reverse centralized extended last mile. And from collection point to warehouse, reverse centralized semi-extended last mile. So these are the different types of last mile. And as you can know that this hyperlocal has become very, very popular now. Now as you can understand, if I go directly to the customer, then we spend a lot of money in delivering. That means I have to employ agents, there is transportation cost, there is fuel cost for those agents, and it's also time consuming. But at the same time, I will come to that discussion. People really want that. People are ready to pay for that. But if I want to optimize, then it's better to, instead of delivering from warehouse to each individual customer, it would be better if I can deliver from retail stores which are in the location, and then I am delivering to the local customers. So some of the companies which are doing grocery delivery and all, in today's context, then you will see them delivering from local retail stores to the different customers. Even food that is delivered from by Uber or by Zomato or Swiggy, this kind of companies, they are actually delivering using hyperlocal services from local restaurants to the surrounding area. So this is hyperlocal. So to look at the growth of this particular last mile, particularly this extended last mile, the advent of e-commerce and home delivery is changing the nature of freight flows drastically in an urban area. So last mile implies the final mile of delivery. It can range from a few kilometers to even 100 kilometers. So it depends on the situation. Last mile logistics allow businesses to ship products to consumers faster and cost effectively, since consumers are willing to pay extra for better last mile delivery services. Like people are asking to deliver same day or instant delivery, because that is how people with money, they will be, they are willing to pay extra. And the requirement of e-commerce to fulfill single orders over large geographical distances with ever reducing lead times is increasing the total distance traveled per unit of goods. So this is a point of concern. That means because I am delivering single orders over large distances, automatically it will lead to increase in total distance traveled, and accordingly emissions and all will be increased. So this is why this last mile, and particularly this extended last mile, has become very, very important in the context of urban planning and also freight management. So this is not freight management in the traditional sense. So this is where an individual takes up your order, uses his own vehicle to deliver it to you. So that is actually sort of we can also say sort of a business trip. So that is either we can put it inside a passenger framework, passenger travel demand modeling framework, or it could be part of the freight modeling framework. So we have to be very careful about that as well. But usually it's very difficult to track a person's trip chain, particularly a person who is delivering like that, because we have to have a subcategory of those kind of services, and then we have to add those trip chains. So instead, it's better to model using a freight modeling framework and to identify this kind of people who are engaged in this kind of activities, and then based on that particular based on the activities of those persons, we can identify what sort of trip chains he forms, and that could be added into the overall amount of travel demand that is generated in an urban area. So last mile logistics is an inseparable component of the growing B2C commerce and presents a near challenge to city logistics. And the last mile is also the most expensive part of the B2C supply chain, because this is individual delivery. So this is also very, very expensive. So home delivery represents one of the most important services rendered by an e-commerce provider. So this part is very important. Your reputation depends on that. And due to stiff nature of competition in the e-commerce industry, players are unwilling to reduce level of service in terms of lead times, delivery windows, and cut cost. So that is where this area has become very, very competitive. And some of the effects of home delivery and e-commerce, like there is increased competitiveness leading to reduced delivery lead times, goods sourced over large geographical distances, multiple sources of collection, multiple points of delivery, lower consolidation of goods. So this is another problem. Larger number of smaller delivery vehicles in cities. So these are the issues that are now arising. And certain other issues which we should also talk about. These are other changes that is coming to this particular industry, like there is Uberization of trucking. That means we can have this logistic companies which are some of them are now like for example, when we are talking about 3PL, this is third party logistics. So these are the logistics carriers. We have discussed the term carriers earlier. So these are these are carriers which can consolidate goods by different senders and receivers, and then they can do the delivery. So these are separate entities. So these are not private goods carriage by a particular company. So these guys are doing insourcing. So that means that they are not only doing the delivery till the warehouse, they are also extending their supply chain and again delivering it to individual customers. So that's why they are insourcing those kind of last mile delivery services in-house. So this is one issue. Data analytics is improving this kind of services. There is a lot of data generated. We can analyze the data to determine best routes for delivery or best locations to locate our consolidation centers and so on. So we will look at both these problems. So how do we locate our consolidation centers as well, or any kind of transshipment center, as well as how do we deliver more efficiently. So then there could be also drone and autonomous vehicle based delivery systems in future, IoT devices and sensors for tracking the delivery vehicles and all, which actually increases efficiency and also generates data, and Uberization of trucking, which actually means we can there are private operators who are having trucks, free trucks, so we can link those trucks with certain requests for goods transfer. So that is what we call Uberization of trucking. So these are the new changes that are also coming into this sector, which also needs to be considered when we determine freight flows in an urban area. Now, as I was discussing, we need to understand what should be how to locate different transshipment centers, or how to determine freight flows between the supply points and the delivery points through transshipment centers or without transshipment centers. So basically, the transportation problem help us to determine these freight flows from the supply and demand without any transshipment. So this is the first, and the transshipment problems is a transportation problem where there is a transshipment center as well. So the transportation problem is one of the subclasses of linear programming problem, and the objective is to transport a single homogeneous product stored at various origins to different destinations while the total transportation cost is minimized. So I have got different distribution centers in an urban area. From which distribution center I will send this particular good to which retail store. So that could be the problem that we are solving. and this is a spatial linear programming problem where cost of transportation is minimized subjected to demand and supply constraint. So that means total amount of demand is equal to total amount of supply, that we can assume. Sometimes it is not, so but we can need to balance that. And sometimes we say that total amount of demand and supply, there has to be balances. And so some assumptions. Sources S1, S2, Sm with capacity A1, A2, Am, like we have discussed in the transshipment problem. Destinations, there are n destinations with requirement B1, B2, and Bn. Transportation cost from ith source to jth destination is Cij, and the amount shipped is Xij. So this is the amount shipped, and Cij is the cost of that particular distance or impedance between the source and the destination. So obviously, Cij into Xij is the total cost, amount into the cost of sending that amount in that particular direction, or that particular this particular route, and then this we sum it over for all I and all j, where I is equal to 1 to m, and that is for all the different capacities that are available, and then summation over I equal to 1 to m, and then j equal to 1 to n, and j is all the requirements. So that means all the different, we can sum it over, and this part is actually an Xij is greater than equal to 0. So these are the two. Aij is equal to sum over Xij, where j is equal to 1 to m. So and Bij is equal to summation Xij, where I equal to 1 to m. So this two actually ensures that the supply, these two are balanced as well. So the two constraints are checked over here, the demand constraint and the supply constraint, and the total cost of transportation is minimized. So this could be shown over here in this particular figure. We have sources first and second. We also have destinations first and second, and this A1 is the amount of available for supply, A2 is the amount available supply at 2, destination B1 is the total requirement at 1, B2 is the total requirement at 2, and Cij, Xij is the total cost of travel for the total. Xij is the total goods transferred from Xij or X1 to 1 is basically goods transferred from 1 to destination 1 to source 1 to destination 1. So that is how we will determine this. So to do that, this transportation problem could be solved in two stages. The first step is to find an initial basic feasible solution, and then step 2 is to modify this solution using an optimality test to find the final optimum solution. So we start with a solution which is possible, and then we, by changing that solution, we can actually, or testing that solution and making adjustment to the solution, we can through an optimality test we can determine the final optimal solution. Now there are three methods. There are many methods actually, but three common methods to find the initial basic solutions are the northwest corner method, least cost method, and Vogel's approximation method. Whereas the optimality test is carried on by using the UV method that we discussed earlier. So the northwest corner method, where the demand should be equal to supply. This is balanced transportation problem. That means the total amount of supply and demand has to be same, but sometimes it is not. So we have to make an unbalanced problem into a balanced problem, and this is possible by introducing a dummy variable. This I will show at the end, that how to balance this unbalanced supply and demand. But to solve the problem, we have to have a balanced problem. So what we do is we create a matrix of amount of supply and demand, and then we know the impedance for each of these particular values, and then we start allocating. So allocating some of these cells, this particular goods that would be transported. So that means we, in case of northwest corner method, we start with the northwest corner. So in a matrix, the northwest corner, if I have a matrix like that, this is the northwest corner. So this is where we will start, and this has, so one side is supply, another side is demand. So there, that means there is a supply constraint and a demand constraint. So we will start allocating that what amount of goods could be allocated over here for which would serve this particular supply, and also that amount of demand would be also satisfied, and so much amount of supply would be exhausted. So that is how we will do that. I will show you using an example. The maximum allocation is made within the supply demand constraint. So we will decide on that, we will put that in the northwest corner. And if I see that either supply or demand becomes 0, then we will strike out that row if supply is exhausted, or we will strike out the column if demand is exhausted. And in the remaining table, whatever remains, we will select again the northwest cell and make possible allocation. So we will keep on doing that till all the demand is satisfied. Let's see an example. So this is the matrix. So this side is supply, this side is demand. So this is the demand, like at D1, this is the total demand is 7, D2 total demand is 9, D3 total demand is 18. Supply, A supplies 5, B supplies 8, C supplies 7, and D supplies 14. So as you can see that 2, 7, these are the impedances or the cost for supplying this from A to D1 or for A to D2. These are the total cost that is there. Now, as you can understand, for over here, that means this is the northwest corner, the first corner, maximum how much I can supply over here. So over here, out of 5 and 7, this is the least value. That means I can do the entire supply over here itself. So that means that means from A to D1 I can supply 5. So that means my entire supply is already taken care of. So I can only supply this particular, and if we supply 5, then in demand out of 7, 5 is already supplied, so 2 is left. So that means for D1 I have to again supply 2 more from somewhere else, but for A I have already supplied entire 5. So A cannot supply anybody else. So there is no point of keeping that. That's why I make it red, so that there is no use of this particular row. So next I again go to the northwest corner. Northwest corner is of course this one. So over here I see that at this side is the total supply 8 and this side is demand. So I can supply the total demand over here. So over here itself too. So that is what we have done over here. And then if I do that, then demand becomes 0, and then this side is 6 amount of supply is still left. So this could be again allocated somewhere else. So we keep on doing that, and then again this is the northwest corner. So I will again allocate over here. So over here out of 9 and 6 I have done 6, and out of once it is done, then we are left with 3. And then this is the northwest corner. Then within 3 and 7 we can supply 3. That is what is done over here. So now we come to this particular step, where the next step, where we see that we have allocated the final values of 4 and 14. So now both the rows are balanced, and we see that this final allocation of 4 and 14 completes the process. And now we see these are the allocated cell. So A, D1. So from A we can supply D1. 5 is supplied. So this is first allocated cell. So this is the second allocated cell, and then from B we are supplying to both D1 and D2, and from C we are supplying to D2 and D3, and from D we are supplying to D3. And if I look from the D1's perspective, I am getting supply from A and B, D2 is getting supply from B and C, and D3 is getting supply from C and D. So total transportation cost is 2 into 5, then 3 into 2, then 3 into 6, 4 into 3, and so on, which gives me total of 102. So this is one solution. So this is not the optimal solution. This is one of the solutions. Now looking into the least cost method, it is almost same as the northwest corner method. The only difference is again the demand should be equal to supply, and when we do the allocation, we start the allocation at the cell which has got the least cost. Everything else more or less remains same. So let's look at the problem. We take the same problem. So over here in this particular cell, the least cost over here is BD3 has the least cost, and which one is BD3? This one. So this has got the least cost 1. So out of all this, so we will start allocating over there. How much we can allocate? So out of 18 and 8, so we can allocate 8 over here. So we can allocate 8. So that is being done. So if I do that, this becomes 0, and we are left with 10 amount of goods that needs to be sent to D3. So we listed 10. In the next step, we find the list cost is again 1 over here. So we will allocate over this part, and then we will allocate out of 7 and 14, we can allocate 7. So that means over here the entire demand of D1 is satisfied. So that means we list 7 over here, and over here D still has got another 7 items to deliver. And then in D3, then in the next step, we find that out of this cells, we have got, this is the list cost 2. So we allocate 7 over here. Out of this 10 and 7, we allocate 7. So we are left with 3 over here. So we keep on doing that, and then we arrive at this step where we see the final allocation of 2 and 7 happens, and the process completes, and then again the allocated cell is multiplied with the cost, and then we come to a value which is 83. So again, this is not the optimal solution. This is one of the feasible solutions, and but one thing to point out is this solution is better than the previous solution. But it may not be for all solutions, but in this particular case, it is better. So then comes the Vogel's approximation method. This method is a bit different, where the demand again should be equal to supply. So we first have to balance the equations, balance the matrix, and we have to introduce a dummy row or a dummy column, and then we calculate the penalty for each column and each row. So the first step is to calculate penalty, and the penalty is the difference between the least two values in a row or column. So we choose the least two values in that particular row, and we take the difference, and that is the penalty, and we do it row wise and column wise. And then if in the chosen row or column, allocation is made to the least cost cell. So whichever has got the maximum penalty, we choose that particular row or column, and then we allocate in the least amount of value or cost value that is there, we will do the allocation. And the maximum allocation is made again with supply demand constraint. This part is same, and when supply is exhausted or demand is, when either row supply is exhausted or demand of the column is exhausted, then that row is strike off, and the remaining table recalculates the penalties. And we will repeat this until all demand is satisfied. So only thing is we will consider penalties. So let's first calculate the penalty. Again, the same problem we are using. So row wise penalty, if I calculate, so this row wise penalty is out of the list two values are 4 and 2. So penalty is the difference between those two. So that is 2. Then that in the next row the list is 1 and 3. Again the penalty is 2. Between the 5 and 4 penalty is 1. 1 and 2 penalty is 1. And if I do it column wise, 1 and 2, it is penalty is 1. Between 4 and 3, again penalty is 1, and 1 and 2 penalty is 1. So that is the penalty. These are the penalties. Now, as I can understand, these are the two are the highest penalties. So I can choose either one of them. Let's choose the first one. So 2 is the highest penalty. So in that particular row, the least value is 2. So we will start allocating at this particular cell. So over here we have checked the supply and demand. So we can supply 5, and then this 5 is supplied over that means D1 is supplied 5 from A1, and the total supply of A is exhausted, so it becomes 0. So this row is unusable. So next we move on, and we again estimate the penalties. We see that the penalties are 211, and this has changed because we have now strike off this row. So this becomes 211. So again, out of this 2, we can choose any one of them. So again, this has been chosen. So over here 8 is being allocated. So out of 8 and 18, 8 is allocated. So 10 is remaining to be supplied to D3, but this supply of B is exhausted. So this is how it is, and then we can repeat those steps, and over here you can see that only these two values remain. All the other rows are already taken out. So these 4 rows are there. So again we calculate penalty. Out of 1, 5, 4, 2, 5, 5 is the highest penalty, and that means we will choose this row. And again allocation is done. So 2 is being allocated over here, and then that leaves us with 5 and 4. and there the penalty is 4 and 2, so allocation has to be done at 4, and that actually gives us the final step, and that directly has to be supplied, and we can supply that, and then we can balance that, like 4 and 2 is there, so this is 7, and so that means we can put values over there, and more or less all values are done. So we have 1 2 3 4 1 2 3 4 5 6. So this is the final step, and we can again calculate the cost, and we can see the cost is 80. So this is again not an optimal solution, but at the same time this is one of the feasible solutions, and again this is lesser than the least cost method. So this is the different 3 methods that we can use to actually determine which of these cells should be allocated, and we can multiply the allocated volume into that particular cost to get the total cost of the this particular transportation cost for this particular system. Now this is the first solution. Let's now do the next step, that is the optimality test, and this we do using the UV method. And the first step in this particular method is to first check for non-degeneracy, that is the number of rows plus number of columns minus 1 should be the number of allocations. So this is the first thing that we need to check. Then we assign the rows values u1, u2, u3, u4 up till um, and we assign column values of v1, v2, v3, v4, vm. And then using of this particular formula, ui plus vj equal to cij. Cij is the cost values for each of those cells that we have already discussed, and we calculate the values of uv for allocated cell using this particular formula, and we start with the assumption that u1 is equal to 0, or we can start like that, and then based on this 0 assumption we can estimate the cost of all the other cells. I will show you that. And once we have done that, then we have to calculate the penalty values for non-allocated cells. So all the non-allocated cells has to be considered. Now as we are starting with a particular feasible solution, already in my feasible solution there are allocated cells. So that already we have to check at the beginning itself. So this allocated cell, and then there are non-allocated cells. So for non-allocated cells we will check the penalty using this particular formula once ui and vj values are calculated, and if no penalty value is less than 0, the solution is optimal. If it is less than 0, then we will continue. What we will do? We will identify the cell with the most negative penalty value, and then from this cell we will construct a loop with alternate plus and negative signs. So this loop will be only done through the allocated cell. So I will give you an example, and this loop is basically, if I suppose there are 4 cells, I will start a loop here, so I will go like that, and then this will finish the loop. So this I will go this way, and this way, and then come back. But all these cells has to be allocated once only, otherwise we cannot form the loop. Now we will also use positive and negative signs. So if I start with this positive sign, then this is negative, this is positive, this is negative, and so on. So we will do with either positive negative sign in this way, and then we will find the cells with negative signs and the least allocation. That means the cells with, suppose both of these are negative sign and has the least allocated value. So we will take that value and we will subtract it from the other cell, that is, and we will add it to the positive cells. So along all cells in the loop, add this allocation to all positive cells and subtract allocation from all negative cells. So that is what we will do, and then we will recalculate UV penalty values. If no penalty value is less than 0, solution is optimal, otherwise we will repeat this entire process. Let's explain through an example. So let's assume this is a initial feasible solution. So we have got A, B, C, 3 supply points, and then D1, D2, D3, D4 are the delivery locations, and these are the allocated values, like A to D1 there is 45, then A to D3 there is 30, A to D4 there is 25. All the costs are also given. From B it is 80, 45, and C that is 75. So we start with we first check for degeneracy, m plus n minus 1 that is total number of rows plus number of columns minus 1. So that comes to around 3 plus 4 minus 1 is 6. So number of allocations is 6. So that is fine. Since no allocations, number of allocations are equal to more than m plus n minus 1, the condition for non-degeneracy is satisfied. So that means we can go ahead. So we also have this formula ui plus vj equal to cij. Now let's start with the assumption ui equal to 0. We can start with any one of the rows or columns, but let's start with ui equal to 0, and then we can see if ui equal to 0 over here plus vj equal to cij. So we already know the cij values for all the allocated cell 1, 4, 3. So immediately we can find vi values. So because it is 0, v4 would be same as this, so it is 1. Then v3 would be same as this, which is 4. Then vd1 should be same as this, which is 3. So this 3 we know, but we don't know this value v2, and we also don't know. V3 value we know and v4 value we know. So now using these values, like we can also calculate for the other allocated cells. So for example, ui plus v1 equal to 3, assuming u1 equal to 0, so v1 becomes 3, and u1 plus v3 equal to 4, therefore v3 equal to 4. So same way, then u2 plus v3 equal to 4, so u2 plus v3 equal to 4, and we already know v3 equal to 4, so u2 is also going to be 0, that is there, and u2 plus v2 equal to 2, therefore v2 equal to 2. So we can just calculate that using the same way, and u3 plus v1 equal to 1, therefore u3 would be equal to minus 2. So now that we know the u values and the v values, using this particular formula for determining penalty for the non-allocated cells, Pij, we can estimate the penalty for this cell, this cell, this cell, this, and this. So when we have done that, we see all of them are positive values. That means there is no penalty value is less than 0. So the initial basic feasible solution is the optimal solution. So we can accept this as the optimal solution. So using this, we can create a estimate the total cost 3 into 45 plus 4 into 30 plus 1 into 25 plus 2 into 80, 4, and so on, and the total value, that is the optimal solution for this particular matrix. But suppose it is not an optimal solution, then what we will do? So over here we will then, as we have discussed, like a loop is drawn starting and ending at the cell with the lowest penalty. So in this particular estimate, the lowest penalty is this one. So we will use this to start, and then we will create a loop. So we have created a loop from PC D2, this is PC and D2, so from over here, and we have created a loop like that. We have gone through only the cells which have been allocated, and we go like this and complete the loop. So we give alternate positive and negative values, plus, minus, and that is that, and then we check which one has got the lowest allocated value among the negative cells. So this 50 is the lowest negative value. So we will take that, and then we will subtract that from this one and add it to both this other two positive cells. So alternate positive and negative signs are assigned to the loop cells, and the cells with negative signs and minimum allocation in the loop is identified, which is 50, and then this allocation is added to the positive cell and subtracted from the negative cell. So once we do that, we get this, where 50 is now added, this is we have added 50 over here, and then we have also added 50 over here. This becomes 0, and this reduces from 250 earlier, like in the last. So this was 250, so now that this was negative, and so we will add another 50, so that's become 200. So 50 is added over here, and this is also added 50. So because we are removing this 50, it has to be balanced. So that's why we are adding 50 and 50 on this side, and this also we are reducing from over here. And this 50 is allocated to CD2, 50 is subtracted from CD3, 50 is added to BD3, and 50 is subtracted from BD2. So this is what we have done. So here we have subtracted 50, here we have added 50. And once we have done that, we recalculate the ui and the u values and the v values. And once we have done that, we estimate the Pij values, and we see that now all are positive and there is no penalty value, and so this becomes the optimal solution. So the optimal solution is that 250 into 1 plus 200 into 2 plus 0 into 6 plus 150 into 5 plus 50 into 3 plus 200 into 3 plus 150 into 2. So this is the final cost and this is the minimum cost. So this is how we solve the transportation problem. Now we have already discussed the transshipment problem. So we will also solve it by converting it into a transportation problem. I will explain that with an example. So we have got two factories. Suppose both this one produces 200 units, this one produces 150 units. These are the two transshipment centers, and this one requires, and we have two customers. Both of them requires 130 units. And the shipping cost is given, like factory 1 to transfer 1, factory 1 to transfer 1, cost is 8, factory 1 to transfer 2, cost is 13, factory 1 to customer 1 directly, factory 1 to customer 1 directly, this is 25, factory 1 to customer 2 directly, over here is 28, and so on. So we have given this unit shipping cost. This data is available with us. We also know the supply and the demand part. And then we have to construct a transportation problem ignoring the transfer point. So this is the first step. So we now convert it into a transportation problem. So we have factories on this side, we have customers on this side. But as we see, this one is not balanced. So this is 130 plus 130 is equal to 260, whereas 200 plus 150 is 350. So this one is not balanced. So the next step is to balance this. So we balance this using a dummy variable. So we balance this using a dummy variable. So over here we added a dummy variable over here. So both of this, there is no supply, but there is a dummy consumption. So there is a dummy demand. So 130 plus 130 plus 90, it is now 350, and now the supply is balanced with the demand. Now once we have done this, then we will add the transfer points and set demand and supply equal to the total original supply, that is 350. So now over here we have factory 1, factory 2, we have customer 1, customer 2. Now we have added the transfer points. So we have added transfer 1, transfer 2, and we have also added transfer 1, transfer 2 in this particular matrix. And so over here we have the costs for each one of that. So this was from earlier. Dummy is given a cost of 0 because there is actually no transfer, right? So that is why that is given as 0. And from each, so this is the data that we have already got earlier. So addition is this dummy column. And total transfer we have also given as total as 350 and 350, and again over in this side this is given as 350. So this is the maximum capacity that we are allocating for this transfer points. That means they can transfer the entire quantity that would be supplied. So once so this is the transportation problem that we need to solve. This is the So this is the transportation problem. So we already know how to solve that. We can use any one of the methods, Northwest or least cost or Vogel's, to solve that, and then use UV method to get to the final optimal cost. And once we do that, this is what we get as the final solution. So we get factory 1 to is getting around sending around 130, and to dummy 20 is going. Actually it is not going anywhere, so because we have, but to balance the equation, that's why it is coming. So in this way, if I see, the final solution is from factory 1 to transfer point 1, 130 goods are being sent. From transfer point 1 to customer 1, again 130 goods are being sent. From factory 2 to customer 2, directly 130 goods is being sent. Transfer point 1 has unutilized capacity of 220, and transfer 2 has got unutilized capacity of 350. So that is what is shown in this particular image. So basically we use the transportation problem to solve this. So these values, we get some values in the dummy, but because it's a dummy, we ignored that in the final solution, and we see that company 2 directly sends goods to customer 2. This is the most optimal, and factory 1 goes via this transshipment center, which is also more optimal instead, and factory and this transshipment point 2 is underutilized. So you can get an idea, like this actually shows us that how to optimize on the supply chain in an urban area, and this could be also used to actually do deliveries in a more efficient way, and this will also give us the traffic flows. That means to deliver 130 goods from 2 to this factory 2 to customer 2, we will exactly know which path will be taken, and we will allocate so many trucks to transfer this particular goods. So this kind of problem has to be first solved to determine what kind of flows will result, and from that we can estimate freight flow in an urban area. These are some of the references. So to conclude, last mile logistics is a growing area in urban logistics, and with B2C commerce increasing each day, last mile logistics is going to be a challenge for both business and urban policymakers. Transportation problem could be used to determine optimal freight flows, both quantity and routes, as well as to solve location allocation problems for setting up warehouses for supplying a market. So we have seen transportation problem and transshipment problem used for determining both freight flows, to determine the total quantities that has to be sent and the routes that has to be taken, and also the total allocation problems, and also setting up of warehouses, size of warehouses, location of warehouses, also this could be determined. Thank you.